All right, welcome calculus students. We're going to be doing the parts of section 4.4, which are on definite integrals. We're going to be finishing the rest of that section to start the trimester 3. So section 4.4 applications, we're first going to do the mean value theorem for integrals. But before we do that, people were saying that in the last videos they missed having a joke or a funny story. So I have to tell you something horrible happened to me today. I was in a meeting, the accreditation meeting, and they had put out this little bowl of candy. And there's like these little mini Snickers, you know, like super mini ones, the size of like a quarter. Anyway, so I was I was a little hungry, so I decided to grab a couple of little Snickers. And so I ate one, ate a second one. I wasn't really paying attention. And so I grabbed a third one and unwrapped it, and there's just this horrible taste and texture in my mouth. I look it down at the wrapper. It's a Three Musketeers with marshmallow. Okay, it's like a special edition or something. Anyway, bad, in my opinion. Yeah, maybe not that funny, but funny enough. All right, anyway, so let's get going. All right, so in section 4.4, we're basically going to be looking at applications of definite integrals. And we're going to start with the mean value theorem for integrals. But first, let's review. So this is going to be a review. The mean value theorem for derivatives. All right. So for the mean value theorem for derivatives, we covered this back in chapter 3. And so if we want to find the average rate of a function, so this is f prime, the average rate on an interval a to b, then this is just equal to the slope of the secant line. So that's going to be f of b minus f of a all over b minus a. And so this is the average rate of the function. So I'm going to write this over here. The average rate being the key word, of f of x on the interval from a to b. Now notice if you're looking for the average rate, then here this is your average rate, and that's going to be equal to the slope of the secant line between the points a and b. All right, so now the next thing we want to do is we want to look at something, let's do this graphically as well. So if I look at this graphically, then if I'm finding the average rate between 2 points, a and b, and this is my function f of x, and I want to find the average rate, which is the average slope of all the tangent lines, then the average rate is the slope of the secant line between points a and b, which is this equation over here in the box. Okay, so what we want to do that's new is I want to find the average, instead of the average rate, I want to find the average value of my function f of x on the interval a to b. So I'm going to kind of separate this out. So I'm looking for the average value. This is the average y value of the function from a to b. All right, so if I have, let's say, some function. So this is my f of x from a to b. Then my average value, my average y value, if I look at all the y values, this is my y value at a and my y value at b up here. Somewhere in the middle, I'm going to have this average value from a to b. Now, in order to figure this out, the first thing I need to do is look at this area in here. So this area, I know this area bound by the function and the x-axis from a to b is going to be equal to the definite integral from x equals a to x equals b of f of x dx. Okay, now in order to define the average value, what I'm going to do is this is going to be equal to, so I'm going to take, and this is how the average is defined, I'm going to take this whole area here. So pretend like this is kind of a malleable area. And I'm going to make it into a rectangle. So if I take this area underneath this curve, and I keep the a and b consistent, so this is my, this is my a, and this is my b. Well, if I take this whole area and I'd make it into a rectangle, then by definition, the height of this rectangle is going to be my average value from A to B. And so these two areas are exactly equal to one another. And so I know the area underneath the curve is going to be the integral from a to b of f of f dx. But the area of this rectangle is the rectangle has a height of the average value, the average y value, and a base down here. And the base of this rectangle is going to be b minus a. So I know that the area of this rectangle is going to be the height, which is the average value of the function, a to b, times the base, which is b minus a. Now, to complete this, what I'm going to do is I'm going to divide both sides by this b minus a and solve for my average value. And so if I do so, then my average value of f on the interval from a to b is going to be equal to, now again I'm dividing out this b minus a to both sides, so this is going to be equal to 1 over b minus a times the integral from a to b of f of x dx. And this is the mean value theorem for integration, or integrals. Now, notice the difference between the mean value theorem for integrals and the mean value theorem for derivatives. For the mean value theorem for derivatives, we're finding the average value of the rate, or you'd be asked for the average rate of a function. And the average rate of the function on some closed interval from a to b is going to be the slope of the secant line. Now, what's different here is for the mean value theorem for integrals, I'm not looking for the average rate, I'm looking for the average value. And so those are the key words there. Is if you're asked for the rate, you'll want to use the mean value theorem for derivatives. But if you're asked for the average value, which is the average y value of the curve, then you want to use the mean value theorem for integrals. And for the mean value theorem for integrals, it's not a rate, it's just the average value. And notice that you're integrating the actual function itself. Okay, so let's look at an example of. And so, for example, let's see, and we'll do this as a kind of a part A. So, for example, part A is I want to find the average value. And this word value, average value, is going to tell you that you're using the mean value theorem for integrals. So I want to find the average value of the function f of x is equal to x cubed on the closed interval from 1 to 3. Okay, let's not do x cubed. Let's do f of x is equal to x squared. It's just an easier function to deal with. Okay, so let's see what's going on here. All right, so I've got my curve, and I know my curve looks something like this. This is f of x is equal to x squared. And I'm going between 1 and 3. Okay, so my average value, my average y value, is going to be somewhere in the middle here. And it's going to be between the y values, and the y values for x squared, f of 1 is 1, f of 3 is 9. So my value is going to be somewhere in between. And the way I find that, remember, is I'm going to take this area, and then I'm going to equate it to an area that's equal, but is a rectangle between 1 and 3. And the height of this rectangle is my average value. Okay, so let's write that equation out. So the average value of f, so the average y value on the interval from a to b, is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, so in this case, I'm looking for my average value of f on the closed interval from 1 to 3. And so it's going to be equal to 1 over, b in this case is 3, a is 1, so 1 over 3 minus 1, times the integral from 1 to 3 of f of x, and f of x is x squared, dx. Okay, so this is equal to, let's see, 1 over 3 minus 1 is 1/2. So 1/2 times the antiderivative of x squared is going to be x cubed over 3. And I'm evaluating that between 1 and 3. So this is 1/2. And you can factor out that 1/3, but I'm just going to leave it in. So I've got 1/2, and then I've got, multiply 3 first. So I've got 3 cubed over 3 minus 1 cubed over 3. Okay, and then 3 cubed over 3 is just 3 squared, so that's 9 minus 1/3. And so that's 27 thirds minus 1/3, so that's 26 thirds. So this becomes numerically 1/2 times 26 thirds, because that's, again, that's going to be 27 thirds minus 1/3, that's 26 thirds. And 2 goes into 26 13 times. So my average value, my average y value from 1 to 3 of this function is going to be equal to 13 thirds, which is going to be equal to 4 1/3. All right, so if I redraw this graph here, here's my graph, and then I'm going to draw the function f of x, which is x squared. I'm just going to draw it between 1 and 3. So here's my value of 1, and here's my value of 3. And so my I know that f of 1 is 1, and f of 3 is 9. And so this is 4 1/3. So 4 1/3 is somewhere around here. And so this represents my average value of all these y values between 1 and 9 on the interval from 1 to 3. Okay, now the next thing I want to do is I want to actually apply the mean value theorem for integrals. And so for part B, I want to use the mean value theorem for integrals to find the x value, or values, where the function f of x is equal to x squared is equal to the average value, not the average rate, but the average value on the interval from 1 to 3. So what I'm doing here is I'm actually looking for this x value where this occurs. And to do this, all I'm going to do is I'm going to set my average value from 1 to 3 equal to f of x, and I'm going to solve for x. So if I do that, then my average value is 13 over 3, and my function is x squared. And so if I do that, then I get x is equal to the square root of 13 over 3, and the square root of 13 over 3 is approximately, using a calculator. That's why I paused it for a moment. Using a calculator is 2.082 using 4 sig figs. So if I go up here to my graph, then the y value of my average is at 4 1/3, and I got that by using the this integral. And then in order to find the x value, if I know the y value, then I just set the function equal to the y value and solve for x. And this is technically, since I'm taking the square root, plus or minus, but in this context, the minus would be outside the given interval. And so this x value right here is 2.082. So it's very similar to using the mean value theorem for derivatives, except here I'm finding the average value of the function and not the average rate of the function. Okay, so the next thing we want to do with this is look at physics applications, which are very useful, of course. And so let's first look at, so let me do the title here. So this is physics applications. Physics applications of the mean value theorem for integrals. Okay, let's first look at average velocity. Now, for average velocity, let's say we're given that my velocity is equal to sine of t on or for t is greater or equal to 0 and is less than or equal to pi seconds. So let's say this velocity is in meters per second. And I want to find the average velocity on the time interval from 0 to pi. Now here, remember, if you're asking for average velocity, if I knew what the position was, my x, then I could use the mean value theorem for derivatives. But since the velocity is given, and I'm asked to find the average velocity, then I'm really finding the average value of the function. So I want to use the mean value theorem for derivatives. So here, the average velocity is going to be equal to 1 over b minus a times the integral of v of t dt from t is equal to a to t is equal to b. Now let's make sure that the units work out here. Okay, so as far as units go, this first part right here, that's 1 over a change in time, so it's going to give me 1 over seconds. And then over here in the integral, that velocity term is going to be in meters per second, and this time term is going to be in seconds. And so a meters per second times a second, the seconds cancel, and that just gives me meters. So I've got 1 over second times meter, and so this does give me meters per second, which is what I'm looking for. So for this particular problem, what I'm going to do is, using the mean value theorem for integrals, is the average velocity is 1 over b minus a, and b in this case is pi, and a is 0. So it's 1 over pi minus 0 times the integral from t equals 0 to t equals pi of sine of t dt. And you just integrate that out, and that gives you your average velocity. Now, one thing that's interesting here is, again, I mentioned that if you're given your position instead of your velocity, and you're asked to find the average velocity, then in this case I would use the mean value. So this over here was the mean value theorem for integrals. But if you're given the position and you're asked to find the average velocity, then it's just more efficient to use the mean value theorem for derivatives. So this would be x of b minus x of a all over b minus a. And the units work on this one as well, because the change in x is in meters, change in time is in seconds, so I get meters per second. Now, interestingly enough, even though this is the mean value theorem for derivatives, and the one over here is the mean value theorem for integrals, these are actually the same equations. And I can prove that because I know that the integral from time equals a to time equals b of v of t dt is going to be equal to, using the fundamental theorem of calculus, is equal to the change in the antiderivative of the velocity. Well, the antiderivative of the velocity is position. So the integral from a to b of v of t dt is equal to x of b minus x of a. And if you look carefully, what I can do is, if I'm looking at the mean value theorem for derivatives, this xb minus xa is actually equal to the integral of vt dt. And so if I make this substitution, I get this exact equation. I just would factor out the b minus a. And similarly, if I look at this equation, I get 1 over b minus a times the integral of v of t dt. Well, this whole integral, just the integral portion, not this circled piece, is equal to x of b minus x of a. So if I make that substitution and bring the b minus a underneath, then I get the mean value theorem for derivatives. So both of these are one and the same. You just have to be careful on what you're being asked for and what you're given. So just to be more efficient, if you're asked for the average velocity and you're given the velocity, I would just use the mean value theorem for integrals, because you're really finding the average value of the function that's given, the average value, average value, average value. But if you're given the position and you're asked to find the average velocity, now you're finding the average rate, the rate. And so if you're finding an average rate, then you want to use the mean value theorem for derivatives. But again, they're one and the same, but you want to choose the one that's more efficient in your particular application. Okay, let's look at acceleration. So if I look at average acceleration, it's kind of the same story. So average acceleration. So if I'm given the acceleration as a function of time on some time interval from a to b, Then the most efficient one to use would be the mean value theorem for integrals. Because I've already got the function, I'm finding the average value of that function. So the average acceleration would be 1 over b minus a times the integral from a to b of the function acceleration dt. But instead, if I'm given the velocity on the interval from a to b, then I would want to use the mean value theorem for derivatives. So then in that case, my average acceleration would be v of b minus v of a all over b minus a. So again, just be careful on which one you're given and what you're given. But this is how you find the mean value of a function, or the average value of a function. And going back to the first page, this is the go-to equation for finding the average value of a function. So make sure you memorize that. It's really important. Also make sure that you know how the units work out, because you're going to have 1 over whatever the units are of b and a, times the units of f of x times the units of dx. And really, another way to look at this for units is that dx is going to have the same units, or if this is dt, is going to have the same units of b minus a. So another more efficient way of looking at this is that the units, the units in terms of this, not the units of this piece is going to cancel out with the units of this piece always. And so when you find whatever this is, you're going to get the units of f of x. Where if you're just finding the antiderivative from a to b of f of x dx, and you're not finding the average, then your units are going to be the units of f of x times whatever units of this dx or dt is. Okay, so that is the mean value theorem for integration in a nutshell. And I shall see you in the next video. I'm going to have a little Snickers bar.